That looks great. Cool. Yeah, so I'm Jeremy. I work at Heroku. I don't really have much to say other than that, but I'm the Node language owner, so if you're pushing Node code to Heroku, I'm responsible for making sure that that works and works well and is a good experience. So if you have had experiences on Heroku and want to tell me about it, that would be great. I love hearing about it. Especially if you've had a bad experience, then I can go fix it. But I wanted to talk today about typed JavaScript. I gave this talk a couple months ago at Node Interactive in Vancouver, and it was about a 30-minute talk, but I went through it at a pretty quick pace. I kind of am enjoying the opportunity to give this in a kind of more relaxed sort of venue. But I've had types on my mind for a while now, like the last couple of years. And the TypeScript talk that we had to start off this meetup made me want to talk about how my thinking on types has changed over time. So like the TypeScript talk was a good talk, and it kind of went over the mechanics of like, oh, this is a string, this is a number, this is an object. But that doesn't really convey the way that I think about types or have come to think about types. So this is sort of my attempt at explaining the way that I try and think about stuff when I'm using types in my JavaScript. So a couple of years ago, when I heard the phrase type system, this is kind of what I thought. Like I kind of grew up on Java and C++, where it was just like very verbose and foo equals new foo, and you just felt like you were repeating yourself all the time. And I never really wrapped my head around the different patterns that you see in the different object-oriented languages like Java. Like you have a friend class that's a friend with another class, or you have an inheritance hierarchy. I never really knew when to make a factory or a singleton or an abstract singleton factory being. Like none of that ever really seemed to click. It seemed just like a lot of ceremony. And I just really wanted to write this. So when I found dynamic languages, it felt really freeing. There was just like no ceremony. What is A? A is 2. Later on, A could be an object. It could be anything. But right now it's 2, and I know that because I can see it in the code. And then you just threw things into objects or maps, and everything was just really just objects and functions. And I can wrap my head around that. It was just, I just felt like I could just go write the code that I wanted to write and get things done. And that was it. Like it felt really freeing. But then sometimes you make mistakes. Like you make a typo, you update something over here, and then you forget that it was used on the other side of the code base, or the code base is shared amongst the team, and you just didn't even know that it was being used. And oops, sorry, I broke your thing. So like you got a new feature, things blew up. When you started running the code, a lot of times these things happened to users in production. But that kind of felt like it's your fault. You forgot to handle a case, you mistyped a word, you misspelled something. The computer is yelling at you because you're not very good at thinking like a computer. But you fix it, you write a test, maybe. You move on, but you continue to feel productive. So it's all sort of worth it in the end. But in the past few years, I've noticed there's this increasing interest in typed languages, and some of them are really interesting. So this is the logo for Elm. If you're unfamiliar, Elm is a statically typed language that compiles into JavaScript meant for the browser. It kind of has its own built-in version of React's paradigm and Redux as well. But it's like its claim to fame is that it has something called a sound type system, and it claims that if the compiler passes, if the type system checks out, you'll get no runtime errors. Like your code will not fail once you deploy it. It might do the wrong thing. The logic still might involve bugs, but it will not crash. You'll never see undefined is not a function. You'll never try and access something that's not there, because the compiler can check that before you even merge in your code. It also has a really good focus on user experience and amazing error messages. It uses that type information to understand what things are and then guide you, which is something that I'm starting to see more and more languages adopt, and I think that's really fantastic. Then there's this language called Rust out of Mozilla. Mozilla is rewriting Firefox piece by piece in this new language. Firefox was written in C++, and they thought, and they could not make Firefox secure enough in C++, or at least this is what they thought. So they had an internal project that sort of gained steam and is now gaining steam in the open source world called Rust, which provides some very interesting guarantees through its type system. It has this system of ownership. So has anyone here ever written like multi-threaded C++ code with like shared memory? If you have, like, it's painful. It's incredibly, incredibly painful. I actually had to do that in college for a class. Sidebar: don't take graduate level courses when you're a sophomore. I remember, like, it was one of these projects I'd been working for 3 days straight, just trying to make the damn thing not crash, and just could not do it. So Rust would prevent that entirely. Like, if you pass off a piece of memory to another thread, and then the compiler will check that you don't write over it until the other thread passes it back to you. And it does this before you run your code at all. It's kind of magic. And then there's the React community is talking about this language called ReasonML, but that's really just a new coat of paint over this really old language, or a couple decades old, called OCaml. But that is also, it's kind of this weird academic language, and I'm not writing a compiler, so it's like, why should I care about it? But even if these are the three that I picked out, but even if you ignore these three, most new languages that seem to have like taken off and gained steam over the past 5 or 10 years have a type system of some sort. So Go is one that's gaining a lot of steam. Swift, Kotlin, Elixir. Even Python and PHP are adding optional type systems, or at least according to my colleagues. I haven't actually checked. And I actually have been trying to think of a dynamic language that has come out and gained steam in the past like 5 or 10 years. Like, Python is really old. So is Ruby. So is PHP. So is Lua. JavaScript has sort of taken off and has like the most mind share, but it seems like there's not really a market for another dynamic language. So it seems like types and typed languages are sort of where our industry is headed. But that's all great, but like, I write JavaScript. Like, our app is in JavaScript. It has thousands and thousands and thousands of lines of JavaScript. So there's two options. The left one is TypeScript, and the right one is a project out of Facebook called Flow. TypeScript comes from Microsoft. And both of these try to write a superscript of the language that lays in an optional type system on top of it. So neither of these is perfect. And when I wrote this talk, I actually chose to write it in Flow because that's what I know and what I'm familiar with. I think that since I wrote it, I've kind of given up on Flow being the winner if there is a competition between the two. I think it's a stronger type system. It kind of gears itself more towards functional programming versus TypeScript sort of gears itself towards object-oriented TypeScript programming. But like, they're not actually all that different. TypeScript is easier to get started with. It has better tooling integration, and there's more like definitions for all of the different open source libraries you use. If you're starting something new, you should probably just use TypeScript. But I've used Flow and really like it. But it doesn't really matter because in this talk, like, everything applies to both Flow and TypeScript. So the syntax is almost exactly identical, and there's only a few places where it changes. But like, don't get wrapped up in the syntax. Like, focus on the ideas. With one caveat is like that only applies if you use TypeScript 2 or greater, and you enable strict null checks, which I highly encourage you to do. Without it, then TypeScript is providing you a lot less safety.
Strict null checks?
Strict null checks. So like, I'll get into it later, but you can have a nullable string or something like that. And by default, one of the reasons that Facebook wrote Flow in the first place was because TypeScript didn't distinguish. Everything could be null. And it wouldn't try and solve that for you. TypeScript only added the strict null checks option after Flow came out. And it might actually be what you want. If you're converting a very like chaotic code base, you might actually not want strict null checks at first because it makes it easier to adopt, but it's something you definitely want to work towards turning on over time because then you'll prevent these undefined is not a function issues. So a few months ago, I was looking at these languages and this is my thinking. All of them have OCaml in common, or at least they were all influenced by OCaml. OCaml being this old, 2-decade-old academic, strongly typed functional language. Rust and Elm both claim OCaml as a strong influence. The first compiler for Rust was actually written in OCaml before it became self-hosting, and then they could write the compiler itself in Rust. But it definitely had, the ideas in OCaml definitely played into the Rust language, although it tries to gear to, it's kind of this weird mix between OCaml and C++. And then Flow is written in OCaml still today. And then Reason is literally just OCaml with a bow on top. It's like they added a new parser for the compiler, and they're working on getting these, like joining in these disparate tool chains. OCaml is kind of funky since it's been living in academia for a long time. That it has like 2 different standard libraries, 2 different ways of doing asynchronous requests, 2 different ways of 2 different compilers that target JavaScript as the output. Like it has 2 of everything. So it's a little difficult to sort of get our hands on, but they're trying to provide a sort of blessed experience. Like we're going to create a unified tool set and make it really easy for beginners to pick up. So I started learning OCaml. There's as well like pattern matching in Rust was inspired by OCaml's pattern matching, and now there's a TC39 proposal. TC39 is the committee that writes the spec for the next version of JavaScript. There's now a pattern matching proposal in front of TC39 that they're deciding on. OCaml has, it's called the pipeline operator. If you've done something like Elixir, you might have seen it. You can use the chain function calls instead of like the dot next pattern you see in JavaScript. And now there's a TC39 proposal for that too. Like OCaml's also had a large influence on JavaScript. So I started learning OCaml, and I started to see why it had been so influential. I'm a rank beginner, but what I found is that the patterns that I was introduced to through learning this other language started to change how I thought about writing JavaScript, and especially the way I thought about using types when I wrote JavaScript. Flow and TypeScript also support enough of the OCaml idioms that I started to write JavaScript with this sort of like OCaml accent, and I kind of wanted to explain what that means. So this talk isn't an intro. It's not going over how to use Flow, but there is, or type JavaScript, but there is some background information that would help you kind of follow the points. So here are just a very few things so that we're all on the same page. So these tools allow you to annotate your code and define types. Here we see that foo is a string. I think this is pretty approachable to most people. But modern type systems are also really smart, and that they can often infer the type automatically. So here, Flow knows it's a string because we just assigned a string to it. And you don't have to litter your code with all these foos. The type system tends to know. And if you need to know what something is, you can generally hover on the name, and the tooling will tell you. So it kind of cuts down on the line noise a whole bunch versus what you might be familiar with if you did C++ or Java way back in the day. You can also give types a name. So this is the syntax. I can alias a type. Here I'm just conveying some extra intent. So if I initialize a variable, I can say this is an email specifically. And this is the syntax for adding types to a function declaration. Because inference is really, really good, most of the time that I'm adding types, I'm explicitly adding them to function calls. Most of my JavaScript files have a couple of type aliases at the top maybe, and then the rest of the types are in the function calls, but then the rest of my code looks very, very much like vanilla JavaScript. There's this concept called union types, and they're very, very powerful. perhaps like deceptively so at first. So you can read void here as the value undefined, and it's the only value that fits the void type. So this might be an argument type for an optional argument to a function. Like maybe it's passed in, maybe it's not. Maybe it's passed in as null. This is so common in JavaScript that there's a shorthand for it. So this is the exact same as the previous slide. So you call this a nullable string. Union types kind of exist in this quantum state where they could be any of the types that exist within the union. So here, string is either null or undefined, or it's a string. But the type system doesn't know and doesn't care. So we can do things that are common to all the types. We can pass all those values around, no problem. I'm not actually sure what else you can do with a null and a string. But if we try and treat a nullable string as a string, so here we're trying to take the length of it, the type checker is going to know that, oh, you can't take the length of undefined. That would cause an error, so that's silly. You don't want to do this. The computer is trying to help you. So it gives us a warning. But if we check to see if foo is truthy, if he evaluates the true, then the type system could do something clever. It knows that within that block, undefined would not have passed the check you just did. So it knows that within that block, you no longer have a nullable string. Foo, if you're accessing foo within that block, it must be a string because it's eliminated everything else. So this is called type refinement. And when people refer to Elm or some of these other languages as having no runtime exceptions, that doesn't come for free. It comes because the type system is forcing you to dot all your I's and cross all your T's. Even if you know for certain that this thing is never going to be null, it will still force you to do that and force you to take care of all of the error cases, which you do grow to appreciate over time, although at first you hate it. But the type system will give this a pass, and you know it's not going to crash. So instead of saying, giving a type as what we think of as a type, like string, number, these primitives, you can also create types that are values. So here, we're using two different values. We're saying anything that's defined as type currency is only either a string that says USD or a string that says CAD, US dollars or Canadian dollars. So we're using this to create what's called an enum. This is an example of a type that the type system can't infer. We're telling the type system new information, and we're conveying that intent to the type system so it can be more thorough and give us additional help. So there's also a type called an object, which kind of works like a magic box. If you use an object type, the system knows absolutely nothing about the contents. I can put things in, so I put a string into an object, right? And I take it out. The type system says, this is now an any type. I don't know what it is. It went into an object, and now I can't track it. There could be proxies. There could be things that are affecting the contents of this elsewhere in the system, and I can't evaluate it, so you're sort of on your own. So you generally want to avoid giving things types like object. Type systems become much more useful if you start to define these structures and break them down. So here we say that price is an object, and it has two different keys. One, currency, which we can see above, has to be one of these two values, and a number. So then now we look at the bottom, and we know that we can see that, oh, this matches the type definition. But if someone tries to set a price that's in pesos, the type system is just going to catch that. And we can make this pass by adding a new option for currency, and then the type system is going to be happy. So you can compose these two features together, the unions and the structuring with an object, with something called a disjoint union. A disjoint union requires that all the shapes that we're trying to decide between have one property in common that's a strict value that Flow can use to do what's called type refinement. Usually it's a string name. Here it's a Boolean. And here's how you could use that. So Flow can use this tag, this success tag, to do refinement just the same way we saw with the nullable string. Within this callback, it knows that if success is true, then result also has to be available. So there has to be a result. Otherwise, the type system would have complained when you created the object. More importantly, if I say result is true, and I try to access error, which only exists when success is false, then the type system knows that that's not actually possible, and it can throw up an error and a warning saying, hey, you're trying to do something that doesn't actually make sense. It's not important to this talk in particular, but like this is imitating a concept that has a name. It's called algebraic data types, although that kind of sounds scary. But so disjoint union, it's just JavaScript.
Will these slides be available after the talk too?
Sure.
That'd be great. That's good. Thank you.
So there's actually a lot more to Flow's type system, and there's a whole lot more to TypeScript. When I look at TypeScript, I get sort of overwhelmed by the number of features, the number of things you can do. But these specific features pack sort of like punch above their weight. If you can use them, you can leverage them to get the compiler and the type system to help you a ton. And I'm sort of like going to go in with an example to try to explain what I mean by that. So when I tried to come up with a concrete example, I thought candy shop. Because why not? Everybody loves candy. So here is this function. This starts out really simple. It's not going to stay simple. You can tell because I've left a whole bunch of space, conveniently. But we're given a count and an item. And the item is an object and has price. So we return count times price. That's pretty simple. So ship that. And we know this won't stay simple because of the spacing in this case. But also, we should never really expect software that we write to stay simple. Software doesn't really exist to be simple and elegant. It exists to serve a function. And it's natural that as you learn more about the users that you're serving, what your customers want, as the business changes and evolves and grows, your code's going to do that too. So don't try and read and understand all the code that I'm going to be putting up over the next few slides. Just kind of watch how it's evolving. So you ship your first version of the store, and it's a great success. Congratulations. Everyone's walking down the sidewalk with like big chocolate bars, and it's beautiful. But then the owner of the store goes to the airport, and they see this amazing candy store there, and their eyes were open to the wonders of bulk bins. So now you got to have this. So this is gonna bring our store to the next level. So our program changes a little bit. Now an item either has a bulk price, a price per unit, or a per item price. And this is still pretty simple. So ship that, it's okay. Then the store decides that they want to run a sale on some items. So like 10% off lollipops and 20% off Hershey's. And our code gets a little bit more complicated. So now sometimes items will have discounts. But the discounts don't apply to the bulk bins. They only apply to the items with single prices. But there's only one more case, so why not? And then that sale is successful, and then business continues. And now we want buy two, get one free coupons for rock candy. So now you have to support a coupon. So now you have a discount type in addition to just a straight discount. And now you need to have special casing for that. And then another candy store opens up down the block. And now we're fighting for our users. We want to make them sure they continue shopping with us. So we set lower prices on some items for members. And that applies to both individual items and bulk bins. And I gave up trying to fit all the code on a slide. We've had this explosion of complexity, and there's a good chance we're going to end up calculating the wrong price for any number of things. I'm not even certain this code is correct, and I wrote it. So we're going to miscalculate a price. We're going to ignore member price. People are going to get upset. Like, oh, no, you're supposed to charge me this. Well, our system says this other thing. And worse, like this item object is not used just in this function. It's going to be all across your code base. We have to know if an item has a discount to advertise that to non-members. We need to know if a special applies to an item to brand it differently. We're going to need to access these properties all over our code base, and it's all going to start looking like this. And it's getting harder and harder to make changes. We're more and more likely to make mistakes. And it's getting difficult to even understand what is item, what even is happening. Like, how many people have worked in code bases that end up looking like this? Yeah. And it's not going to stop. The business keeps moving. So like, you're going to start supporting multiple currencies, and then what happens? You're going to offer the discounts that apply to the cart as a whole, like buy these two items and together and save 10%, and so on and so forth. Like, none of this is unreasonable. Like, sometimes as programmers we're like, no, this is going to like ruin my code. It's going to look ugly after you add this. Or like, I don't even know what's going on anymore, so I'm going to like push back against product. No, we got to slow down. Like, there's too many errors. What we really have is like a failure to deal with the complexity that we've started adding to the product. Our language isn't helping us at all here. And if we start looking at the type of item, we kind of see why. Every single property now, as this has evolved in item, is now optional. We don't know if any of them are there. So we can have a price that doesn't actually make any sense. So member price, it has a member price, but it doesn't have an actual price, but somehow it has a unit type because maybe it's a bulk bin, but it's sold in kilogram. I don't know. Like, the type system is just completely okay with this. Or what if we accidentally assign a discount when it doesn't make sense? Like, can you have buy two, get one free with bulk bins? Like, is the cashier going to be there like counting out jelly beans? Well, I guess I only weigh 2 out of every 3. No. The type system's still fine with it, though. Whereas, like, everything is optional, so an empty object is still just fine. Like, how many times have you been debugging something, and then you're just like, where did this object come from? It doesn't actually make any sense in our application, or it's just completely empty. Like, who created that? Something came out of the database, and I don't know. Let's just add an if statement here and hope it doesn't happen again. Or you just go through and add a whole bunch of log statements trying to figure out exactly which thing created the object that doesn't make sense, and it's hard. So, and then if your code is structured like this and you type it like this, that thing where the type system warns you if you're trying to do something with a nullable type is going to drive you up the fucking wall. Because every time you try to access any property of this item object, it's going to say, oh, that, and you try to use it, it's going to say, oh, that could be null. So you're just going to be adding if true, like if not null, everywhere in your code base. And you're like, why did I even bother trying to pick this type system thing up in the first place? It's just nothing but headaches. So there are better strategies. So taking a cue from OCaml and some other strongly typed languages, there's a piece of advice for cases like this. You can leverage the type system to make illegal states impossible to represent. And I'll just kind of show you what I think about that. So one thing to notice here is that there's a whole bunch of relationships that are not encoded in the type. And they're not anywhere in our code. They're in our programmers' heads. So we shouldn't have a member price without a non-member price. That makes sense. That's logic. But it's nowhere in our code base. It's being enforced haphazardly throughout our code base, but it doesn't exist encoded there at all. And if we have a bulk price, we should probably know what unit we're measuring. And while we're at it, we should probably enumerate all the different types of weights that we support, like ounces, pounds, kilograms, whatever we support, whatever is valid within our store, we should probably spell that out. And then, what discounts are there? Can an item be both on sale and priced at buy two, get one? Our previous example would have been fine with either of those options. And we just have to know or have maybe a comment somewhere. So let's see what we can do with a type. So we're returning to flow. We're trying to define a type. We're going to sort this out. We start out with just a price. And now we have an extension point where we can add bulk bin pricing. By using a union, now we have a clear separation. Pricing info is either going to be one of these or the other. It can't be both, and it can't mix the two. We also added unit types to define that we support ounces and pounds. We can conveniently add membership price now. And now it's clear that one, may or may not be there because we marked it as nullable. And two, it only applies to individual item prices. And we can enumerate the discounts that we could offer and the data that each one needs. So now we have a percentage discount that needs a discount value. And then 2 for 1, which doesn't need that value. We just know how to apply it. But now we could have other things that apply in different ways. And it's also really clear now from the code how we can start to add new things. If next week we start offering rentals of cotton candy machines, we can add a rental type that is different. And now this information is encoded in our type system, and now it will warn us. So if someone tries to build this same object that doesn't make any sense, now we get errors, which is great.
What is this construct called? The pricing info with the or operand?
In Flow, it's called disjoint union. I don't know what they refer to it in the TypeScript documentation as. It's some combination of union or sum type or algebraic data type. But it's like there's only a few concepts we're playing with here, but it gives us a lot of power to make the computer do work for us. So
when it's type single, the first one has to match for the rest of them.
Right.
To match. So it can only be type single or type bulk, and then from there, those other ones are inferred or declared, I guess.
Because I have type single, like Flow knows that it has to be in that first branch, and it uses that type value. So if I said type bulk, then here it would throw an error. And actually, it's going to throw an error here too because it says type single, and it has a member price, which is nullable, but it doesn't have a price, which is not nullable.
You can't mix and match the things. Once you're in one, you're in. It's got to be exact.
Yeah. But like you're going to be passing around your code, and it's just going to be a value, and then you're going to treat it as something that's sort of like in this quantum state. Like I'm passing around one object, but if I want to actually access price, then the type system is going to make sure that I refine it and make sure that type is single. So that it knows like, oh, it's in this branch. And now inside this block, I know that what properties are available, what aren't. And if they shared concepts, so like if they had, so if price was shared between both different types, and I'm accessing price, it won't throw an error because it knows that that's safe to do because they share this common property. So here we have a member price with no price. The type system catches it. If I change it to price, then it's gonna say it's okay. I think as far as I'm aware, like it's actually now, given this type, impossible to represent a price info object that doesn't match our business rules. If we try and create one, our system is going to yell at us. And now this additional structure means that writing a function like calculate price is actually a lot more straightforward. And if we mess up, this type system is going to catch it. And notice that we didn't have to make any classes. We didn't have to inherit anything. There's no implements, foo. There's no like inherit from this other thing bar. Like this is just a little more than a dozen lines of code, but it serves as documentation. It conveys intent, and it enables the type system to do a lot of work for us all throughout our code base. And it doesn't take much time to write this. So there's another idea that sort of goes alongside this that comes from these type languages I want to talk about. I was first introduced to this idea when I started reading about Rust, but it was in OCaml before that. Haskell has a similar concept, and who knows where it actually came from. But the idea is code for exhaustiveness. We should structure our code in such a way that the type system can tell us when we've missed a case, when we're missing something. So this is Rust code. And match works kind of like a switch statement. Match comes from OCaml. So instead of using the string values that we were showing in Flow, Rust has enums as the first class properties. So I define this enum named color, and it has red, green, and blue. Those are the only options. And we can use match to branch on this value. You can kind of think of color as like a Boolean with 3 values. Like Boolean has true or false. Well, what is true? What's the value of true? It's true. Instead of true and false, this has red, green, blue. And there's an important difference between match that in Rust and switch in a language like JavaScript or C or C++. If the match isn't exhaustive, if it doesn't go through every single possibility, like if we get to handle blue here, it's going to tell us. It's going to tell us which case we didn't hit. We'll get an error. Yeah, Elm has really, really good error messages for this case. But we can make it harder for the type system to help us. So in Rust, if you're doing a match and you want a sort of else clause, you can put in an underscore. And it says, OK, if it didn't match anything above this, then it hits this branch. So now we have the same switch statement. But what if we add a new option? So someone comes on, like a new feature request comes in, and now we have to add crimson as a new color. Well, now the type system is still OK with this. Like all of this still passes just fine, even though crimson is definitely red and it now printing out not red. So now we can file a bug. Because our type system is we've kind of made our type system unable to help us in this case. But if we make sure that we extensively list all of the possibilities, so in this case, instead of the else clause, we take the little bit of extra time to write out the other possibilities. Now, when we add a new color, we added this new case, our type system is helpful again. Now it's going to say, oh, now over there, you didn't take care of this case, and over here in your code base, and over there. So if you try the same thing in JavaScript, now the type system is happy, even though we didn't cover every option. It turns out that neither Flow nor TypeScript support exhaustive matching, and that makes me very, very sad. But you can, if you're diligent, you can fake it. So Flow has this special type called empty. In TypeScript, I believe it's never. And this might have changed in the months since I wrote this talk. I thought I saw that TypeScript might support exhaustive matching, but I'm not sure. Well, let's say that it doesn't, or you have to force it this way. So no types satisfy empty. It's like asking for a type that satisfies being 1 and 2 at the same time. It just doesn't exist. There's nothing that satisfies it. So the syntax here is basically an assertion. It's saying we're asserting that the type is empty. We're asserting that nothing can reach this branch with a type for color. So if we do this, then the type system then sees that blue is going to hit that path, and it's going to throw us an error. So this is not quite as good as it is in another language because you have to be diligent and annotate your branches this way. But if you do, you get some good benefits. So let's see how this might play out back at the candy store. So we're offering machine rentals. Cotton candy machines are just always a huge hit at children's parties, and we want in that racket. So now we have this really logical place to extend it. We add a new type rental, and I'm aligning it for simplicity, but any data that it needs. And because we've been diligent about coding for exhaustion, we start to get errors. We get an error in this function that we were working on, but also we get errors all across our application. Anywhere we're accessing data that's stored in this pricing info object, the compiler is going to start yelling at us that, hey, no, there's something new. And now I add one branch to one type, and I now know every single file that I need to go update. I won't be able to forget them because the type system is going to be telling me where I need to go. So I don't have to hold the system in my head anymore. I can just change something and then let it tell me, and it's sort of a relaxing sort of change. Something you do after lunch. It's like, oh, let's see. Okay, I'll fix that one, and then that one, and then that one, ship it. Versus like, okay, let's see. Who is accessing this? Where is it going to be? Where's that logic? It's much nicer. So these are coded as errors, but I think that's actually sort of a misnomer. Like I kind of think of it as just like errors are your like type system's way of telling you it loves you and wants you to be happy. Like this was when I sort of came to this realization. It was something new to me. Like I was used to a compiler or a type system being this final step. Like I'd go and write the thing, and then I would go and add all the type annotations, and then it would yell at me, and then I'd have to go and fix it. But I don't know, like this changed the way I write code, and the compiler started becoming my friend. Recently, I've been doing a lot of work in Python, and I used to love Python. And Python is a great language. It's really easy to learn, get people started. But my feeling now when I'm writing Python code is that the computer is just sitting there being lazy. Like I run something and it's like, oh, this thing doesn't exist. You had a typo. I'm like, well, computer, like you have the brain the size of a planet. You're sitting there doing nothing to help me right now. Like you know what's going on. You know that doesn't exist, but the language doesn't really support that level of tooling.
Congratulations, you have created Marvin.
But like type systems, are like you're using a lot of very complicated math to help you ship whatever you're trying to do. And it's not to say that I love them. Certainly, I hit my frustrations where I'm trying to do something complicated and it's hard to model that. But now I have a new appreciation for what I'm buying when I'm spending that time fighting with the type system. So if this was interesting to you, I highly recommend watching this talk by Yaron Minsky called EffectiveML. I think he's presenting it to a class of students at Harvard who are learning OCaml as part of their course. You don't really have to know or know anything about OCaml in order to follow it. If you followed this, you'll probably do great. But the ideas are really interesting. I stole some of them for this talk, but there are others that I couldn't really include. And that's it.
That's great. Thanks.
How has your workflow evolved as you've gotten more, or like gained a deeper understanding of types? You said like you used to in the beginning, just like fill out all the types at the end.
Yeah.
Has that changed a lot?
Sometimes no, sometimes yes. It's just now I think of it as, we can turn on the lights. Now I think of it as another like tool in the toolbox that I can reach for. So there's some times where I find that thinking through how the types are going to change changes how I think about how I'm going to approach the problem. And other times I'm like, oh, just get the thing done, and then I go ahead and add it because I already know how I'm going to solve it. But it kind of just goes back and forth. And that is actually like makes TypeScript and Flow quite nice because it supports either way. But as anecdata, I recently, or a couple months ago, I wrote a simple little service. I think it's like maybe about 800 lines of Node. And I made sure it was like very thoroughly flow typed because it's in the critical path of deploying Node on Heroku. When you deploy a Node on Heroku, I need to know which version of Node to install, and there's a symvar matching feature. So I have a server that knows all the different versions of Node that have been released and is watching for new ones. And and it goes and matches and pulls it down. I've received 0 runtime errors. It's been happily working in production without breaking down in the 8 months that it's been up. And I was kind of terrified because what if I mess up? Then, oh, now thousands of people are deploying and they're not getting, it's failing. So I definitely felt very, very thankful for the type system. And there's this sort of like bulb flash moment that people talk about when learning like a Haskell or an OCaml or anything like that, where I write the code and then the type system yells at me, and then I go and dutifully fix all the different things, and then my code runs the first time. And I sort of had that experience. And yeah, I was like, oh, I want more of that. It's great.
I know like VS Code has like a one for TypeScript. You guys want similar or whatever?
It does, yeah.
Okay.
The ones for VS Code are great.